Okay, in this phase changes video, we're going to talk about the phase changes, all right? So most substances actually exist in 3 states of matter, depending on what temperature they're at and what pressure they're at. You know, we looked at before, there's actually a 4th and a 5th state of matter, but we're only going to talk about the changes between 3 of them, okay? And energy is either added or removed from a system. One phase will change it to another. So if we're talking about energy, we're usually dealing with heat, or energy in the form of heat. So if I heat something up, a substance up, it might, melt and then it'll vaporize. It'll change from maybe a solid, then to a liquid, to a gas. If I cool it down, it might go from a gas to a liquid to a solid, depending on what the temperatures actually are. So the first one we're going to look at is melting, because that is usually an easier one for people. Okay, melting is you're changing from a solid to a liquid. So we're going from very close together to a little bit further apart. Well, anytime you have to go from something close together, something a little bit further apart, all right, you are pulling things apart. Well, if you're pulling them apart, you've got to put energy in to pull stuff apart. And what are you pulling apart? I'm pulling apart this molecule from this molecule, okay? So they're no longer very close together anymore. And the stronger of the bond that you have between these two little molecules, okay, the higher the melting point. So the stronger the bond you have, the higher the melting point. Something that has a very large melting point, okay, maybe thousands of degrees, is going to be something that has a very strong bond between molecules. And again, we're looking at between 2 molecules. So I'm talking about if I have a molecule here and another molecule over here, okay, these are actually connected together. Okay, otherwise you would have little separate like Dippin' Dot type things. But if I say have water, all right, I have a water molecule, another water molecule. You're breaking the bond between 2 water molecules, all right? And the stronger it is, the more heat it takes, the higher the melting point, all right? Vaporization, okay, is where I'm going from a liquid to a gas. So again, I am going from something that is, a little closer together. So liquids take my whole container here to something that is a little bit further apart, more spread out. So again, the heat is going to break bonds apart, okay, and the molecules escape to become a gas, all right? So I'm going again, the heat going to break your molecules apart, or one molecule apart from another. Now you have a couple of words again with vaporization, okay? We're dealing with what's called a vapor pressure, all right? Vapor pressure is the pressure a gas creates, or the vapor creates, on top of a liquid. So we see this container over here to the right, all right? As something starts to vaporize, okay, I have a liquid, you add heat to it, it becomes a gas. As it starts to become a gas, all right, the gas particles that are there exert a pressure over your liquid, and that's called a vapor pressure. Now, when does something actually boil? Okay, something actually boils, all right, when your vapor pressure, this pressure above this liquid, equals whatever the atmospheric pressure is. We do BP for boiling point, kind of MP for melting point, is when your vapor pressure equals your atmospheric pressure. So if my atmospheric pressure is different, then your boiling points are going to be different. So if I am at in Denver versus if I am here, the boiling points of substances are going to be different. Because if I go over to Denver, all right, which is higher up elevation, which means I have less little air molecules exerting pressure. So someplace I'm going to write that. So Denver has a low atmospheric pressure. Okay, I'm going to put AMT pressure there. So it's going to have a much lower boiling point. Because my pressure over top of my liquid doesn't have to be very much to equal whatever is around it. So water boils at a different temperature in Denver than it does here in Archbold. Okay? And there's a whole chart to decide how or when something will actually boil. But this is what it's saying here on the right. Okay? Below the boiling point, the pressure on the atmosphere, which is my red or my blue, what's red on the chart, okay, is not equal to the pressure above the liquid, which is the black lines there. Okay, eventually it starts to boil and bubble, okay, and they'll actually be equal. When they're equal, something is actually at its boiling point. Okay, the vapor pressure, or the pressure above the liquid, has to be equal to your atmospheric pressure. All right. Now, vapor pressure and intermolecular forces. Okay, you see IMF here. We'll talk more about those at the end of the year. Okay, but all I mean is by that is your between two molecules. So now we're talking about how vapor pressure goes along with the attraction between two molecules. Okay, if you have a large attraction, meaning they really want to stick together. Think of two magnets that are really want to stick together. Okay, they really don't want to be apart. So they had a really strong attraction. You're going to have a really small vapor pressure. Okay, and you're going to need a bunch of energy to become a vapor. And it just makes sense. Like I said, think of it with magnets. If you have two really strong magnets that want to be side by side, okay, it takes a lot of work to separate them apart, which means you're not going to have much of the stuff that's separated. So you're not going to have much of a vapor pressure. If you have a couple of molecules that are not really strongly attracted to one another, then it's not going to take much heat to really heat them up and get them to break apart. Whereas large attractions take lots and lots of heat to get them to be pulled apart. Okay? So those are all dealing with vaporization, which is again liquid to a gas. Okay? Sublimation is pretty cool. All right? And you're going again from close together to further apart. You're going from a solid to a gas. So I'm going from a solid, so really close together, to really far apart. Okay? You totally skip the liquid phase altogether. You give this thing so much heat, so much energy, it goes right from being a solid to a gas. Okay? Dry ice is probably the best example of this because you go dry ice sublimes, going straight from a solid brick all the way right to like the fog or the gas of that one. You need a lot of energy to do this because you're totally skipping your liquid phase. So let me clarify, you're totally breaking bonds here when you sublime. Okay, go from a liquid to a gas. If you go with their vaporizing, you're totally breaking two molecules apart. If you go from a solid to a liquid, you're just stretching your bonds apart. All right, you're just stretching them and seeing how it goes. Okay, those all require energy, so you're going from really close together to really far apart. Now we're going to look at the three phase changes that go the other way. Okay, basically just have a different name. So these are all going to be releasing energy. If you have dew on grass, okay, in the morning, or a little condensation on the outside of a glass of water on a hot day, those are both where you're releasing energy. They're just opposites. Okay. Start at the top. The easiest one, freezing. Freezing is going from a liquid to a solid. So I'm going from further apart to closer together. Okay. Your molecules are losing kinetic energy. Remember, kinetic energy is just a fancy word for energy of motion. Since they lose kinetic energy, the attractions between molecules start to kind of pull them back together. You can think of it almost as a tug of war. Your molecules have lots of energy by themselves, but they're also attracted to one another. Well, if they have too much energy when they're by themselves, they like to be apart, and the attractions between them don't win. But if they don't have much energy to motion, then when they get side by side, they tend to stick, and they find somebody else and they'll stick, and they find somebody else and they'll stick. So the less kinetic energy they have, the more likely they are to kind of stick together, and those attractions between molecules will kind of pull them back together. Same thing goes for condensation, except for condensation is when you're going from a vapor to a liquid. Okay. You can say vapor, you can say gas. Technically, it's a gas if it's in that state at room temperature. Everything else is really called a vapor, but I let you use them interchangeably. But again, it's the same thing as freezing. Okay, you lose some energy and you're going from a vapor to a liquid before we're going from a liquid to a solid. Okay, deposition is because you're depositing, all right? And this is the last one. It's gas to a solid. Okay. If you're going from in the morning, okay, it's really cold outside and your car has lots of frost on the outside, that is deposition. The really cold air met your warmer windshield stuck to it and became a solid. It went from being a gas to a solid. So the best one there is probably water vapor on a cold windshield. Again, you're just losing lots of kinetic energy. All right. The last thing we're going to look at here are phase diagrams. Okay, and how to read a phase diagram. So I'm going to talk about what they are, and then I'm going to show you some different points, and then I'm going to show you how to read it. Okay. Phase diagrams just show the different phases that occur based on a temperature or a pressure. Remember I talked about not all boiling points are at the same spot. Water doesn't always boil at 100 degrees. It depends on where you're located in the country or in the world, what your elevation is. Okay. Same thing goes with temperature. All right. You can have some lines on here, and all points on lines are where you have two phases coexist. So a line on this lovely graph or diagram here is where you have two phases that actually exist at the same time. Okay, so let's look at some important features of this graph, and then I'll kind of explain a little more about the graph itself. Okay, we have what's called a triple point. Triple point is where all three phases exist. You have a critical point. That's where you can't tell the difference between a liquid and a gas, which may seem weird, but it is. All right, between your solid liquid, you have the melting line, because it's melting. It's also called the freezing. You can look at it either way. You're either going solid to liquid, you're melting, or the other one is freezing. Doesn't matter, freezing or melting line. And if you're looking at between a liquid and a gas, those are either called the vaporization line, a boiling line. You could technically go the other direction and call it a condensation line. Nobody just does. All right. The other key term here is the word normal. If it says normal, that means at 1 atmosphere, which is kind of like what it normally is on a day-to-day basis. It's pretty much 1 atmosphere. It fluctuates, but for the most part, things are at 1 atmosphere. Okay, so let's take a look. This is a phase diagram for water. Okay, water has 3 sections: solid, liquid, gas, or vapor. Okay, so solids are always the lower left, liquids are in the upper right, and vapors are on the bottom. Okay, you have pressure on your y-axis. You have temperature on the x-axis. Okay, any point in here, I'll know that water is a solid. Okay, so if I am less than 0 degrees Celsius, and I am, say, at 1.5 atmospheres, which will be, somewhere around there, all right, I know that I will be, as water, it will be a solid. If I heat water up and say, okay, I'm gonna look at water at 60 degrees Celsius, because these are degrees Celsius. So 60 might be somewhere in here. So I'm at 60 degrees Celsius and 100 atmospheres. Well, 100 would be somewhere up here. I'm in the liquid section. So I know that right there, water is a liquid at that temperature and that pressure. All right, it's just like reading any other graph, okay? Your triple point is here where all 3 exist. All right, they're where all 3 lines cross. A normal freezing point and a normal boiling point. You can also call it a normal melting point, okay? It's at 1 atmosphere, wherever 1 atmosphere decides to cross the solid liquid line, and where 1 atmosphere decides to cross the liquid gas line. Whatever temperature that is, all right, that is where something will boil at a 1 degree or 1 atmosphere. Okay, but as soon as you change, the boiling point changes. So if I say, okay, I'm up in Denver and I'm not at 1 atmosphere, I'm at 0.75 atmospheres, so I'm somewhere down here. When are we actually going to boil? Well, I look across. Where do I meet it? I meet it somewhere down here. So water in Denver boils at say we're going to call this, I don't know, 90 degrees. Okay? If you get a higher pressure, water will boil at a higher temperature. Okay? All the way up to where you get to a critical point, or you cannot tell the difference between a liquid and a gas anymore. You have such a high temperature, such a high pressure. Molecules are really close together, moving really, really fast. You don't know. Those are called a critical point, right? And the 2 lines actually start to blur, okay? And every molecule and product or compound is different, all right? This is just water's diagram, all right, based on the temperatures. You can have you can do this for carbon. You can do this for any other compound you come across.